Dr. Carlson, a theoretical physicist here at the Purdue Quantum Science and Engineering Institute. Welcome to Quantum Connections, where we have interesting conversations with people working on all things quantum. I'm super excited today to have as our guest Dr. Richie Wunderlich. He is an electrical engineer who is a founding member of a startup company, IC Analytica in Austin, working on making computer chips better. And he also happens to be my brother. So we have known each other for some time, but we're not going to tell you how long. Welcome. I'm so glad you could join us. This is true. We're still not going to tell you how long. So one of the things we like to ask our guests is what got you interested in being an engineer?
I think I was fortunate that my family really helped with that. So, of course, our father was really good at trying to encourage creative understanding about how the world worked, right? And then, then you did as well. And some of it, from my perspective, is I don't feel like my brain came with like a really good way to memorize a bunch of things. So, for my ability to sort of like cope in school and just trying to understand the world, I felt like if I could learn like a few basic things and then just kind of derive my way up from there, right? Then that helped me be able to like navigate the world, right? I particularly remember enjoying geometry when I first took that because I was like, well, I could probably decompose everything into just right triangles and get my way done, right? Or I could have learned some clever tricks along the way to get to the answer quicker and so on. So just an insatiable curiosity about like just how everything works. So some of that was born, some of that was just encouraged by my surroundings, and so I'm appreciative of that. Yeah.
Cool. And this thing you're talking about, like really clicking with geometry and this feeling of like I could probably do everything with right triangles. There's like a feeling of, I think, power that comes along with when you understand something. It feels really good, and you feel like, man, I could go like conquer the world or invent stuff.
Oh yeah, absolutely. Yeah, it did feel right.
Yeah.
And it was fun to just sort of like try to test your ideas against that kind of stuff. Because you could try to make a claim about something in geometry from some sort of higher level intuition for whatever reason that you have, and then go test whether or not it was correct, right? And I found out I could even do this like during tests, be like, I think this is a way to solve this problem. And like, oh, I have more time to try to like verify that with like more lower level stuff that I know that I trust more, that's just more tedious, right? To get to the answer. So
yeah, that's cool. And what you're talking about is kind of also a little bit of a, not quite democratization, but everybody's kind of on an equal footing when we come up to the sciences and engineering, and that truth is truth. And so like you were talking about, you had a few basic principles, but then you can just use them to discover new things.
Yeah, that's right. Yeah. It was fun to get into physics. And the joke about high school physics or whatever is like if you write down epicals MA, you get some sort of partial credit. But you can start there with some calculus, work your way through most, right? Most of the physics that you encounter. So it's really fun. It's really cool. I found that really rewarding, right? And I found that type of academic pursuit way more rewarding than trying to memorize a bunch of things. And because I felt like I was empowered, as you were saying, I could learn a couple of tricks, try to apply them in a bunch of ways, see how they worked out, and then kind of have this idea like, whoa, this is probably applicable to a bunch of other things as well.
Very cool. Of course, I resonate with a lot of those ideas, and we could talk for hours. We're going to keep this just a little bit shorter than our normal conversations of hours and hours ranging until 3 a.m. So can you tell us a little bit about your company and what you're so excited about? What caused you to like start a whole new company for this thing that needed to be done that hadn't been done before?
Oh yeah, sure. So we skipped some steps on the way to the company, right? But going through grad school, I ended up doing a PhD in electrical engineering, and it was in sort of alternative computer architectures, neuromorphic, neural analog compute, asynchronous digital, that sort of thing, everything in the kitchen sink. From there, I ended up in industry, trying to do whatever I could find that I thought was interesting in industry, especially dropping into a big company like I did at Qualcomm. I was fortunate enough to get into sort of what they considered the silicon test chip space, which is where you might get to try out crazy ideas about, we have this idea that if we build a chip this way, it'll compute this function better than before. Or the other things that people tend to be doing in the test chips, particularly at where I was in the type of industry where we do these kind of designs, is we're trying to vet the next greatest fabrication process. So there's this classic thing of how do we try to make chips better, and you can either try to come up with better architectures, right, or try to use your transistors in a more clever way, have a more clever topology for them, or you just try to get better transistors. And that's what we've been doing with Moore's Law. It's like every couple of years or something like that, fabrication processes come along that allows us to build tinier transistors that, in a really surprising way in engineering, usually engineering stuff doesn't go this way. Pretty much every single metric is improved by having tinier transistors. They're lower power and faster. You almost never get that kind of trade-off. Is that usually if something is faster, you do it by consuming more energy or something like that. So just by always going to these tinier transistors, everyone's getting better designs. Don't improve your design, just put it in a better fabrication process and you get a better design. So that's the kind of work I was in, that sort of space. That space is large, but we were at Qualcomm, or I was at Qualcomm with some of my colleagues that we formed this company with, doing this kind of work. And the details of what we were trying to do is sort of what we would call probably electrical metrology, which is how do you measure things about a process? Like when the fab comes up with, like, TSMC or Samsung or Intel says, hey, we have this new fabrication process and it's going to be tinier transistors than the last time. And you go, okay, let me try to get my design into this new process and measure it and see how it does, right? If it works or doesn't work, it's a very, very complicated debug of like trying to figure out why it didn't work. Did you mess up your design? Did the people fabricating your chip mess it up? There's billions and billions of transistors in there and orders of magnitude more wires. So trying to figure out who's up.
Sorry, orders of magnitude more wires than billions?
Yeah, yeah.
Okay,
Yeah.
I guess that makes sense.
The same
'cause
trend.
you've got to connect them all.
Yeah, the same transistor,
Yeah.
the fan out of what transistors, like
Okay.
one transistor tends to drive a signal to multiple other transistors and
Yeah.
so on, right?
Wow.
And so it's probably not 10 times, it's probably not 100 times as many, but you have more.
Yeah.
And then when you talk about what a wire is, a
Right,
wire
right.
is a pretty abstracted sort of simple concept when you're, I guess, in school, or when
Yeah.
you're designing your circuit, you don't want to care about the wires. You want to care about the active components like transistors, right?
Yeah.
And you say, well, this transistor connected to this transistor over here, and you just draw like a line on a piece of paper. And you're like, this means that this potential is exactly this potential over
Yeah.
here, right? And when you go try to build those two transistors with that wire in a modern fab, what you end up with is hundreds and hundreds of like fabrication steps over months to get there, but to build that. But at the same time, you're building billions of transistors and other wires as well. But just that little example, that wire might be very complicated. It might go through multiple different layers to get there. So that wire itself might be, you might consider it, from our perspective of how good are the wires, right? We would consider there to be a lot of wires connecting these two nets because it goes on one layer, hops up to another layer, goes around.
Okay, and you're talking about layers of silicon, right?
Well, yeah, so these, yeah, technically not silicon, but when you think of a semiconductor, the base layer is silicon, that's where the transistors are. The layers on top of that are the wires that we use to connect those transistors together. Those tend to be metal.
Okay.
Yeah, but the whole thing is what we consider the semiconductor picture, but only the bottom part of it is silicon.
Okay.
Yeah.
Okay.
So
Nice.
so we're in there trying to figure out, so like I said, electrical metrology.
Okay. Yeah, we're interested in a couple of things. We'd like to hear what you do with your startup, but also since it's a quantum channel, we're going to get to as well. Where's quantum coming up in your engineering, and does it help you? Does it harm you?
Sure.
All that stuff.
Sure.
Yeah.
Sure. Mostly harm, I would say.
Okay.
There's some devices that don't work without it, so we can talk about that in a second. But yeah, so the general task that we have been working on is how do you vet, how do you analyze these transistors and these wires and these new processes? Because you get a chip and you try to test it. Did it work? Did it not work? If it didn't work, is it because of like one little wire in there? Is it because like one transistor, right? Things aren't necessarily on a binary of this wire either works or this wire doesn't work. There tends to be this wire was better or worse than this other wire and so on. And so trying to tease out exactly what happened is very hard. And
so this is an issue every time someone designs a new integrated circuit with billions of transistors. You go through this process.
Yeah.
Okay.
Yeah. So there's a sort of a classic struggle between the way we partition up this building these things. Fabrication plants get really good at building these wafers and the chips that you ask them to build. And so they tend to offer these services to other people. So we have multiple companies out there that do these designs of these chips, but they don't fabricate it. So like Apple, NVIDIA, AMD, these companies design chips, but then they send those designs to like TSMC or Samsung or possibly Intel, something like that, and they fabricate it. And at the end of the day, they fight over why it worked or it didn't work, right? Did you mess up your design?
Oh, yeah.
Did you not meet the spec that you claimed you would meet, right?
Was it on the design side or on the fabrication?
That's right. So there's this, they fight each other, but then also there's just like a lot of room for collaboration between these two things, right? So the way that you try to diagnose these is pretty archaic and ham-fisted, right?
Okay.
But it's just the best we can do. There are really, really detailed ways to try to figure out exactly what your transistors look like. You can slice up the wafer, you can do like scanning, tunneling electron microscopy on it, and you can get really pretty pictures. It's completely destructive. You can't put it back together and then keep testing. Like I said, billions of transistors, so you can go look at one.
Yeah.
And you look at like the
That's kind of
cross-section
tedious.
of a piece of it. Yeah.
Yeah.
So we are trying to do what I was calling electric microscopy. So like,
Okay.
what is it that we can tease out about how good the transistors and wires are through electrical measurements?
Okay.
And that ends up being, again, a hard thing. So that's why we have a startup for it. There's you have this issue of if you just want to like measure a transistor in a new process, you could build a chip that does that. The transistor is a 4-port device. You could wire all those ports to pads, probably get them up to something that you could actually probe down with like, some sort of needles, attach it to machines that are very good at measuring things, okay? But to measure that transistor, I probably had to use a bunch of other wires in the process to get there. So it's like I wanted to impersonate this transistor, and I know that this process is going to be noisy and maybe not super reliable yet. Or ultimately, I'd like to figure out the statistics of what it looks like when I fabricate a billion of these transistors. What's the mean? What's the standard deviation, and so on. And so it's just very expensive. So like I said, you can make a 4-port device, you wire it to pads, you can do you can do measurements techniques like Kelvin connections. It's a way to have multiple wires come to the same point, and you use the fact that you're only going to drive current through one wire to get there, and then use the other wire to sense what the voltage ends up being. And so because of that, I don't necessarily ahead of time need to know how good those wires are.
Okay.
And then I can get down to what I want to measure. But that takes so many things. So like one little tiny transistor needs to be propagated up to these pads that are massive, and they use a lot of pads. So now you
would still just measure one transistor at a time, and you have billions of them.
That's right. So we're in the business of trying to perform lots of these measurements, right? And because we like to measure, possibly billions of these things, right? Measure them quickly, and then measure them in a way where we actually use the infrastructure of that process, the wires in that process, the transistors in that process, to do some of our metrology, like selecting things, propagating currents around, propagating voltages around. So how do you use a process that you don't trust when you don't know the answers to the process as part of the infrastructure for measuring other parts of your process? Right? So that's what we do, and that's what our startup is currently in the business of. Yeah.
Okay. Okay. So you accelerate then this design loop between the people fabricating the design and the implementation of it, and then there was some troubleshooting to do, so you make that troubleshooting happen.
Essentially, yes.
Better.
I mean, it is one of those things of like more data is just better for people at pretty much any stage of the game, which is before you design, while you're designing, or after your first design comes back. You tend to do a thing of get silicon out the door, and it's going to be okay. Maybe, right? But probably not going to make you a lot of money. You iterate on that design a little bit so that your next version of it will yield a lot better. And you'll be like, yeah. So so at every step of that way, more data about what's going on is useful. Right?
Nice. Nice. Well, talk to us a little bit about where quantum intersects your world. And again, is it helping? Is it hurting? What are the constraints?
Yeah, I would say, when quantum effects show up, for us, it tends to just be if the effect is big enough, do we need to model it, right? And because we're driving to really, really, really tiny transistors, right? and the currents are getting tiny. And, you know, the way you model it should probably be charge-based, and it's probably not being modeled that way.
When you say charge-based, do you mean individual charges
Mhm.
one by? Is that what you mean,
Yeah.
like little
Yeah,
counting
yeah,
electrons kind
yeah.
of thing? Yeah.
So you can't simulate a whole chip with
Right.
with our best models for how
Yeah.
you would simulate it, because
Yeah.
you do like 3D simulations of
Yeah.
transistors. But those are very tedious. And so how do you simulate something with 1 billion transistors?
Right.
It's all about making compromises along the way, right? Or making the right sort of compromises. So whenever we shove in some sort of quantum effect, like it probably needed to be a kind of a strong effect. There's what I've been talking about so far, for the most part, is quantum effects that are not necessarily useful. It's just like we tried to build the transistor smaller. We're seeing these other effects that are happening. Some of the things, like some little instances of that would be stuff like as you bias the gate of a transistor, that's the part of the transistor that shouldn't be pulling any current, but controls the other terminals and how well they are at
Right.
pushing current. You get band bending from the silicon through the gate, and you were at a place where the bands bend in a tight enough fashion that right next to the gate, we can't consider that like a continuous distribution of like electron levels anymore. So we have to discretize them, for
I see.
instance, right? And that just helps us model.
And
It's
that
just ever so.
discretization is quantized, which means it's a quantum effect.
And so that's one where we're not trying to leverage quantum there or anything like
Okay.
that. That's just as we try to get things smaller and smaller,
Yeah.
there's a couple places where a quantum effect might show up, where if we do it this way, our models for the transistors are better.
Right.
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 And that just, again, will, to a designer who's using these transistors, just be some sort of like scalar offset at the end of the day for how the transistor performs, probably. But of course, there are other places in semiconductor devices that actually have to use quantum effects to get them there, right? And we all, I mean, the most ubiquitous of all those is flash technology, which is the industry dominant non-volatile technology out there, right? And probably where most of the bits in the world are stored. That's definitely wrong. I'm sorry, it's trending towards it. But just like, you know.
Well, so there's like flash memory. This is what I would know as flash memory.
Yeah.
And is that like when I'm using my thumb drive, or is that what's on my laptop or whatever? Where is that in my ecosystem?
For the most part, if it's a memory device that doesn't spin. Okay. And if you turn it off and you turn it back on, and it remembers what it had, the state it stored, that's almost guaranteed to be flash technology these days. Yeah. And what flash technology is trying to do is try to take a transistor and modify its behavior in a temporary way. And transistors have, as I mentioned a moment ago, a gate that sort of mediates whether or not current flows through the source and drain particularly well. And there's this idea of like the threshold of the transistor. A lower threshold makes the current higher, and higher threshold makes it lower, and so on. And you can adjust that threshold.
And these would be threshold voltages, right? Okay.
Yeah. And that would say basically something like, how much charge do I need to put on the gate to maybe cause like the channel to invert or something like that in the transistor to get it to source a lot more current. And if you can get extra charge trapped near the gate, right, that changes how much charge you actually end up having to put on the gate to get to the same sort of current level as before. And so flash transistors do this thing of having what they call sort of a floating gate, which is a series of capacitors, right, where that middle node doesn't have like a traditional way for electrons really to get there, because there's a barrier between that node and the other electrons that's higher than the energies that the electrons tend to have, right? And so if you can get charge stuck on that node, it modifies how the transistor behaves, and it will, for the most part, stay there, right? And so the way that you would get the charge on or off that node tended to be apply voltage that was really high to cause something like maybe Fowler-Neumann tunneling to happen through that oxide. So get the bands to bend enough that now you don't see this full width, you start to see this triangle barrier, and then more and more voltage makes it thinner and thinner and thinner, and then they start tunneling through.
So that's using quantum tunneling to write the memory and erase the memory. Yeah. Very cool.
Yeah, and so that's
cool.
That's, I mean, absolutely, there's no classical way to do that, and that's absolutely, that's not like quantum is a parasitic effect that we're just having to model. It's like,
yeah,
this device would not work without quantum,
yeah.
without these quantum.
Quantum is essential to the design of flash
Yeah.
memory.
Yeah.
Yeah, and
Yeah.
I think pretty safe to say we probably all use that every day.
Absolutely.
Multiple times. Very cool. Very cool. Well, tell us a little bit more about Moore's law. And are we, so for me as a physicist, I keep thinking Moore's law has got to end at some point, because if we were getting faster and faster computer chips by making things smaller, at some point you make things smaller enough and you're going to hit hard physical laws such as an atom, right? You definitely cannot make a transistor smaller than an atom. But a
Yeah.
transistor is a device that depends on, a semiconductor having a certain doping level, meaning you've added extra atoms in a certain percentage, we've substituted some atoms in a certain percentage. And so really I feel like once you get down to that length scale of I have a dopant atom here and a dopant atom here, that's game over. You definitely can't make it
Sure.
smaller than that. How close are we? What are the length scales at which we're currently able to fabricate transistor features? And how close are we to just saying that that's it? We can't make them reliable any smaller than that.
Yeah, I mean, everyone has predicted when Moore's law was going to die has been wrong,
Okay.
right? But everyone has always been correct that it seems like it's going to have to be slowing down, and it has been slowing down, right? And as we know, it's not any sort of physical law. It's just sort of a guideline for stubborn engineers to be engineers and scientists to be trying to tackle over time. You go like, man, if in 2 years we can make them half the size, won't that be great? Because half the size is almost twice as fast, half the power, and so on, right? So as I think I described it as more like Moore's almost empty tube of toothpaste at this point, which is
Wait, think about it. I see what you're saying. Yeah, it's like you can always squeeze.
you think you have to buy new toothpaste tomorrow or next week for certain, and then 2 months later you're still squeezing that out. So that might actually be where we are with Moore's law, right?
Awesome.
But the barriers are things like that you talked about.
Yeah.
That as they do get really, really tiny, these are some real fundamental challenges. The thing that tends to be limiting us on the way to too small is just fabrication techniques. Can you pattern? Can you do lithography that allows you to make these patterns as small as you want?
Right.
And that has been a huge challenge, and the industry has gotten by up until very recently, patterning things much, 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 much smaller than the wavelengths of light they were using. It wasn't until recent years that they switched to like 19 nanometer light with extreme UV.
Whoa.
It was like 190 nanometers before that.
Yeah.
Right. So now we've got this huge leap forward in being able to like start fabricating things smaller and smaller again. And we have all these tricks that we were using before when the wavelength of light was really large that we'll bring back like as we need it to push things smaller and smaller. But of course, what you just talked about was things like I have silicon. I'm going to make the silicon like a small area of silicon. And I like that silicon to be P-type or N-type, a little bit more electrons or a little fewer electrons in it so that, it can pass current. And you dope it, right, with very small quantities of things. We've already run into limits of how doping affects our transistors. So channels of transistors, which are the smaller, one of the smallest features in a transistor, and the channel being the part that kind of like constrains or lets the current through. We don't dope those anymore.
Okay. Because they're too small.
It's too small, yeah.
Okay.
Because to dope it the way that you'd want to, you're looking at a transistor like that one may have had one dopant atom in it, that one may have had 2 or 3. Yeah.
Wow.
So these are the things.
And the difference in your design specs between having, or rather the operation of the final thing, whether it's got 0, 1, or 2 or 3 dopant atoms in such a small space, those are just different devices.
Very different.
So that's I understand why you wouldn't dope that anymore.
So what's happening right now? I'd say the biggest challenge to getting the most out of Moore's law, because we keep making things smaller, and we'll continue to make them smaller for the rest of my life at least. Right? Is the variation of them is getting that much worse, because as you're saying, we fabricate a transistor, and now this one might have 1, 2, or 3 or 4 dopant atoms in it, and that's a very, very different device. And the vast majority of the way computation takes place in the world uses a paradigm called synchronous digital design. And synchronous digital design tries to,
This is the idea that like my computer's clocked, is that it?
yeah, that's the
Okay.
synchronous part of it,
Yeah.
clocked. Yeah. And you take sort of unreliable transistors or hard to model transistors,
Yeah.
where transistors with a lot of variation. You wire them in this topology called, that implements Boolean algebra, CMOS logic implements Boolean algebra, and they end up being very, very robust functionally.
Mhm.
So you put in a set of inputs that are just voltages, and then the output voltages will for the most part end up being functionally correct.
Mhm.
You know, if you have a multi-bit function, the output will be the correct set of the
Mhm.
bits that you expect. But how long it takes for it to get to that answer
Okay,
is the part that becomes very, very hard to model.
I see,
Okay.
okay.
And what you can do
Mhm.
is kind of to guarantee that it's going to work is just wait longer,
Mhm.
wait longer and longer and longer. Okay.
And now we don't have Moore's law anymore.
You don't have
We're not
Moore's law
getting
anymore.
faster, we're getting slower.
Well,
Wow.
yeah, and so what's happening with Moore's law, or what's happening as we build the transistors smaller, the variation gets higher.
Mhm.
And so you imagine that the average performance of a transistor
Yeah.
would be amazing.
Yeah.
But it's the tails in that distribution that we have to design around.
Yeah, got
We
it,
have to design around these slowest transistors.
right.
And so
Right.
that's what really keeps us from like
Yeah.
continuing to leverage the benefits of
Right.
the scaling. Yeah.
So it's sort of like if you were gonna run some race with like 10 people and you won the race when all 10 people finished, then you're only as fast as your slowest runner,
That's right.
your team.
That's right.
It's not the way people typically run races, but
That's
yeah,
right. Yeah, yeah.
it's that sort of thing. That's
Yeah.
interesting.
Yeah.
Okay, very cool.
Yeah.
Well, it's been awesome talking with you. Really appreciate you being our guest today on Quantum Connections.
Thanks for having me.